Okay, can you see the screen?
Yep.
Okay, so I start. Okay, thank you, and thank you to the organizers for the opportunity to give this talk. And today we'll talk about viscosity solution for parabolic equation with an application to random time dynamical system. It is a joint work with Rossana Capuani, Luca Di Persio, and Yuri Kondratiev. Okay, the talk is basically divided into two parts. In the first part, the main part of this talk, I will analyze the concept of viscosity solution. So giving the first definition, some model examples we are interested to, and then we will study a theorem of existence in the uniqueness of solutions, and we will see some further estimates for the functions for the solution U. And in the second part, we will see an application to random time dynamical systems. So we give the basic definition we will need, and we will study the asymptotic estimate of the viscosity solution under a random time change, a specific random time change. Okay, so first, the theory of viscosity solution was introduced by Pierre-Louis Lyons and Michael Green-Crandall in 1983, and was born in order to generalize the concept of classical solutions for partial differential equations. Okay, why it is important to generalize this concept? We will see that this is useful in these two examples. So in the first one, we have our model of dynamical system. So we have a flow capital X, which starts from small x, and satisfy this ordinary differential equation with B, the drift term of the system. So if we consider a function f, we consider the function u, we define the function u as f evaluated at the flow, one natural question is, what is the equation solved by u? Okay, in the smooth case, the answer is quite simple. We have this proposition. So if b and f are smooth function, then the function u defined, as already said, solves a first order PD, which is called the transport equation. So the equation is the following, with the same drift B and with the initial condition f of x. And the proof that the transport equation is satisfied in the smooth case is quite easy. So we can compute the derivative of u with respect to time, which is the gradient of f scalar product with the derivative of capital X, which is b evaluated at x. Then the right-hand side is computed in the same way with the Jacobian here of x. And the term in black are equal. So in order to prove that the left-hand side and the right-hand side are equal, we have to prove that the terms in blue are equal, so that this function, which is the difference of this term, is equal to 0. Okay, we compute the derivative of phi using the equation satisfied by the Jacobian of x. Of course, we obtain this equation by differentiating the equation of the dynamic with respect to x. And we prove that phi satisfies this ordinary differential equation. And if b and f, b is smooth, this equation admits only the solution phi equal to 0. And so the proof of the transport equation, the representation formula is done. Okay, a little remark, this computation holds in case of autonomous drift, so without dependence on time. In case of non-autonomous drift, the computation fails and the transport equation fails to be true. A simple counterexample is the following. So in dimension 1, if f is the identity, if b is defined as t plus x, then we can compute easily the solution of the dynamical system. And so u is equal to capital X since f is the identity. The solution is the following. We can compute the derivative in time. We have 1 plus x e to the t minus 1. We can compute the derivative with respect to x. It is just the exponential, e to the t. And so the equation is not satisfied, of course. Of course, we can talk about classical solution and viscosity solution for the equation with coefficients depending on time, but we will not have the representation formula given before. Okay, then we can also consider a generalization to this model. So we can perturb the dynamic with a Brownian motion, and the ordinary equation becomes a stochastic differential equation, where we have a drift term sigma and diffusion term b, and sigma, of course, is a matrix, and capital B is a standard d-dimensional Brownian motion. Okay, of course, if sigma is equal to 0, we obtain once again the dynamical system before. So, so this example is just a generalization. And if we define here U as the average of F computed at the flow, and of course, in the smooth case where B, F, and sigma are smooth functions, then U solves a second order differential equation called Kolmogorov equation. So the equation is the following. We have also a term depending on the Hessian matrix, and A is defined as sigma sigma star. A sketch of the proof, we can give a sketch of the proof here. The semigroup property of the Markov processes and so also of the stochastic differential equations implies that U at time t plus h starting from x can be seen as the average of U which starts at the capital X h. And then using the stability results of the stochastic differential equation, we can prove that U with respect to X is a C2 function in the space variable. Then we can apply Ito's formula to this equality, and we obtain that these increments is equal to this integral. Then we can divide by H, we can pass to the limit for H which tends to 0. We obtain the time derivative here. Here the dynamic x converges to its initial value, which is small x, and so we get the Kolmogorov equation. Of course, also in this proof, in order to prove that U is a regular function, a C2 function, we need some regularity assumptions on B, F, and sigma. So the question is, what can we say if F, B, and A are not differentiable, but for example, are just Lipschitz functions? In that case, we have to exploit the concept of viscosity solution. So we have to generalize the concept of classical solutions. Okay, in order to work with viscosity solution, we need a change of variable, a technical change of variable. So we replace the function U with e to minus lambda t U. And the Kolmogorov equation becomes the following one with this additional term, lambda U. We refer to this equation with the Kolmogorov equation with lambda. And this additional term will be useful in order to prove our result of existence and uniqueness. Okay, and now we have to give a suitable definition of viscosity solution, but first we need to define the superdifferential and the subdifferential of U. So a generalization, if we want, of the differential. So the superdifferential is denoted by P2 plus of U at the point T0, X0, and consists in the set of all this of this point, AP capital X. A is a time viscosity derivative. P is a gradient, represents the gradient in the viscosity sense, and capital X represents the Hessian matrix. So this point belongs to the superdifferential if for Tx, which is close to T0, X0, a sort of Taylor expansion holds holds just from above, so with the smaller or equal sign, and this Taylor expansion in the first order in the time variable and in the second order in the space variable. Similarly, we can define the subdifferential as minus the superdifferential of minus U or if we want, we can give the same definition with the reverse inequality, so with the greater or equal here. Okay, once defined the viscosity solution, once defined the superdifferential and the subdifferential, we are able to define a notion of viscosity solution. We split this definition into two definitions, viscosity subsolution and viscosity supersolution. Okay, I underlined here plus infinity because these computations are done in the unbounded domain, also in time. So this definition, we will give an existence and uniqueness result for all time t greater than 0. Okay, so we give a definition of subsolution. Function u upper semicontinuous and bounded from above is a viscosity subsolution of the Kolmogorov equation with lambda if u at initial time is smaller than f of x, and then one of the following equivalent conditions is satisfied. So the first one, we require that for each element of in the superdifferential, then the equation is satisfied with the smaller or equal sign, so it is satisfied from above, and with the derivative replaced by the elements of the superdifferential. So the time derivative is replaced by a, the Hessian matrix is replaced by capital X, and the gradient is replaced by P. Of course, the definition of the super solution is similar. So we require that U is lower semicontinuous, is bounded from below, is a viscosity super solution if the reverse inequality here is satisfied at initial time, and here the reverse inequality is satisfied for each element of the subdifferential. We can give also similar and equivalent conditions, which was the original definition given by Crandall and Lyons. So we have that U is a subsolution if for all function phi smooth such that phi minus u attains its minimum value at tx, then the Kolmogorov equation is satisfied from above with the derivative of u replaced by the derivative of phi. Of course, u is not a regular solution, so we cannot compute the derivative of u, but we can compute the derivative of phi, which is smooth. And eventually, a bounded continuous function is a viscosity solution if it is both a subsolution and a supersolution. So this is the definition of viscosity solution. First of all, we have to check that this definition is well posed. What does it mean? It means that we have to check that this definition coincides with the classical one in the classical case. So we have to check that if U is a classical solution of the Kolmogorov equation with lambda, then it is also a viscosity solution. The proof is quite easy. If we consider a function phi such that phi minus u attains its minimum value at tx, if u is a classical solution, then we can also compute the derivative of u. We have that the derivative of phi coincides, the first order derivative coincides with the derivative of u in time and in space. The Hessian matrix has the good sign. So the Hessian matrix of phi is greater than the Hessian matrix of u in the metric sense. And so since A is elliptic, the equation is satisfied from above. Of course, with maximum value, we can prove that it is satisfied from below, and so U is a viscosity solution. Okay, then we have to check the reverse. So if we have a classical viscosity solution, then it is also a classical solution. So the two definitions coincides. And this proof is, if we want, easier because it is immediate to see that if a viscosity solution is C1 in time and C2 in space, then the vector given by the free derivatives belongs to the superdifferential and the subdifferential. So we can use here, instead of APX, we can use the free derivatives of U, and we obtain the classical equation satisfied from above and from below. Okay. Then we have to prove that we can pass from the Kolmogorov equation to the Kolmogorov equation related to lambda. In general, of course, in the classical sense, we can do, because it is just a change of variable. We have to check that this change of variable is allowed also in viscosity sense. So U is a viscosity solution of the Kolmogorov equation if and only if V obtained with the change of variable, E2 minus lambda TU, is a viscosity solution of the Kolmogorov equation related to lambda. We skip the proof, which is quite easy. Then, before start to with the computation and the theorem of existence and uniqueness, some related literature. As regards viscosity solution, we already said that the definition was given by Crandall and Lyons, which studied the first order problem in the elliptic and parabolic case. Then Bardi and Capuzzo Dolcetta studied the elliptic first order problem, and Suganidis studied many cases of elliptic and parabolic first order problems. Then the two main articles we will refer in this talk are by Crandall, Ishii, Lyons, which studied the elliptic second order problem, and Ishii, Lyons, which exploits some further regularities for elliptic second order problem. And then Guy Bars, which gives many examples, many cases of elliptic and parabolic second order problem. Okay, as regards random time change, surely I have forgotten some names because it is not my main area of research. But of course, we refer to Kochubey, Kondratiev, and Da Silva in order to, as regards the long time behavior of the random time change. As regards the relation between the random time change and the fractional equation satisfied by the solution with random time change, we refer to Kochubey, Kondratiev, and Piatnitsky, Toaldo, and Zizina. And also as regards the fractional equation unshown, Leonenko and Pirozzi. And as regards the study of the long time behavior using Cesaro mean, we refer once again to Kochubey, Kondratiev, and Da Silva. Okay. Now we can start with existence and uniqueness of solution. A fundamental step in the viscosity approach in all the viscosity proofs for existence and uniqueness consists in the so-called comparison principle. We state here the comparison principle. So if we have U and V a subsolution and a supersolution of the Kolmogorov equation related to lambda, we suppose that F is bounded and satisfies a Holder condition. Sigma is a Lipschitz function with the sublinear growth, and B is satisfies the same hypothesis of sigma, so Lipschitz with sublinear growth, or B is a continuous decreasing function. One of these two conditions has to be satisfied. Then if these hypotheses are satisfied, then U is smaller than V. So a subsolution is always smaller than a supersolution. Okay. A first direct consequence is the uniqueness of solutions. So there exists at most one viscosity solution for the Kolmogorov equation. Actually, if U and V are solutions, then U is also a subsolution and V is also a supersolution. So if comparison principle holds, U is smaller than V. We reverse the role of U and V and we get that U is greater than V, and so U is equal to V. Okay, we give a little sketch of the proof for the comparison principle, which is a readaptation of Crandall, Ishii, Lyons, which studied the comparison principle in the elliptic case. Also, there is also a generalization in the parabolic case, but just for the Dirichlet condition. So now we studied in the whole domain Rn. Okay, with the change of variable, we can restrict to the case lambda bigger than 1, but sufficiently large. We will decide the size of lambda at the end of the proof. Okay, we argue by contradiction, so we suppose that U is strictly greater than V for a certain point Sz. Then we consider the maximum point T bar, X bar, Y bar of the following quantity. So U minus V we have a doubling of variable here. So u depends on x, whereas v depends on y. Then minus this function, which we call phi, and it has this difference from x minus y, and two coercive terms here, one in the space variable and one in the time variable, in order to have that the maximum is attained in our n. Okay, then we have that the function, the maximum value here, it is greater than the quantity evaluated at the value s, z, z. So these terms disappear. We obtain u minus v minus these other terms. And since u is greater than v, for nu small and alpha large, we obtain that also this quantity is strictly greater than 0. Which implies that phi is smaller than v at the maximum point, and in particular, this term here is smaller than u minus v at t bar, x bar, y bar. Okay, what is the idea now? The idea, in the elliptic case, the idea is to use v minus phi as test function for u, and u minus phi as test function for v, because, for example, v minus phi is smooth with respect to y, with respect to x, sorry, because v doesn't depend on x. But in this case, we cannot do a proof like that, because we need, in order to use this as test function, we need also that a regularity in time, and it is not regular in time. So we have to readapt this idea, and we use Jensen's lemma. And by Jensen's lemma, there exists this constant a, c, capital X and capital Y, such that a plus c is equal to nu. So a plus c is the derivative in time of phi. And then this quantity belongs to the super differential and the super differential of u and of v. So we have here the gradient of phi. X and y are not the Hessian metrics of phi, but they have the good sign here in order to work. So since u is a subsolution and v is a super solution, we can substitute the term in the subdifferential and superdifferential here and obtain that these two inequalities are satisfied. Then we subtract the two inequalities. We obtain a plus c here, which is equal to nu. We obtain lambda u minus v here. And this term is crucial. This is why it is important to work with the Kolmogorov equation related to lambda, smaller or equal than the rest of the terms. Okay, we compute the derivative of phi and we can estimate the right-hand side term in this way. So with x bar minus y bar square here we have nu plus lambda, and we use this estimate to u minus v, this estimate here. So we replace with the alpha absolute value of x bar minus y bar square. And we have this additional term here, which tends to 0 when alpha tends to infinity. So if alpha is sufficiently large, we have that omega alpha can be smaller than nu. And then if lambda is sufficiently large, this other term becomes greater than this other term. So we obtain a contradiction for alpha and lambda sufficiently large, and we prove the comparison principle. Okay, once proved the comparison principle, what is the general approach in order to prove existence of solutions? If comparison principle holds, and if we are able to find a subsolution V and a supersolution W of the Kolmogorov equation such that this subsolution and supersolution coincides at initial time and coincides at the boundary if we have also a boundary condition, then there exists a unique viscosity solution of the Kolmogorov equation. Okay, this is the general approach, but now we want to give a direct proof of existence, which allows us also to prove a representation formula for the function u. Okay, so the theorem is the following. We suppose that F, B, and sigma satisfy hypothesis of comparison principle. Then there exists a unique viscosity solution for the Kolmogorov equation. And then we have this representation formula. So if capital X solves the stochastic differential equation, then U can be expressed as the average of F computed at capital X. And then we have a stability results. So if we have Fn, Bn, and sigma n uniformly bounded and uniformly Holder or Lipschitz, Holder for F and Lipschitz for B and sigma, according to the hypothesis of the comparison principle, with Fn, Bn, and sigma n converging towards F, B, and sigma uniformly, then we will have a convergence locally uniformly of Un towards U. Okay, some comments about this existence result. Of course, if sigma is equal to 0, and so the matrix A is equal to 0, we have an existence result for the transport equation. And as a direct consequence of the stability, we are able to prove the vanishing viscosity limit. So if we have U epsilon solution of this Kolmogorov equation with diffusion epsilon, in this case B and F are frozen, the diffusion epsilon converges to 0. So using the stability, U epsilon will converge to U, where U is a solution of the transport equation. So the vanishing viscosity limit is a direct consequence of the stability result. Okay, we give a little sketch of the proof for the existence. Of course, if F, B, and sigma are smooth functions, we have already proved the existence and representation formula. So we need to prove all just in the general case. In the general case, we consider an approximating three approximating functions, Fn, Bn, and sigma n, which converge uniformly to F, B, and sigma, which are smooth and uniformly bounded and with the regularity we need. And okay, of course, since Fn, Bn, and sigma n are smooth, we can have the related solution capital X n and Un, because they are related to the regular case. And we can prove that Un is globally bounded. This is easy because Un is the average of F evaluated at Xn, of Fn evaluated at Xn. Since Fn is uniformly bounded, so will be Un. Then using some Gromwall's estimates, we can prove that capital Xn is locally uniformly bounded. Then we can prove that the dynamic Xn satisfy a Holder condition in time and Lipschitz condition in space, also locally, but uniformly in n. And the same also for Un. Un satisfies a Holder estimate in time and space, where the Holder coefficients depends on beta, which is the Holder coefficient of F. Okay. Now, since we have these estimates, we can apply Ascoli-Arzel's last theorem, at least locally, and we obtain the existence of U and X such that Un converges to U and Xn converges to X locally uniformly. Then we can pass to the limit in the formulation of Xn and Un, and we get the representation formula. Okay, so the representation formula is proved, but we also have to prove that U is a viscosity solution. Okay, in order to do that, we take a smooth coercive function phi. It is not a restriction to assume that phi is coercive, because we are interested just in the local behavior of phi and not in the global behavior. So we consider this function phi such that phi minus u achieves his strict minimum in Tx. So then we consider the minimum of phi minus Un. Since phi is coercive and Un is bounded, this minimum is attained in some point Tn xn. And we prove that up to subsequence, Tn xn converge towards Tx. Then we can use phi as test function for un. Since un is a solution and so it is a subsolution, we have that the equation of un is satisfied from above with the derivative of un replaced by the derivative of phi. Then we can pass to the limit. We can pass to the limit and we obtain that also the equation of u is satisfied with from above with the derivative of phi. And so u is a subsolution. Then we use the same strategy in order to prove that u is a super solution. And so we obtain a solution of the Kolmogorov equation. Okay. And in the same way, we obtain the stability of solutions using the same approximation method. Okay. Now, once proved the existence and uniqueness, we can strengthen our hypothesis on f, b, and sigma in order to gain more regularity for the function u and for the space variable with respect to the space variable. So the two regularities we want to prove is a global Lipschitz regularity and a global semiconcavity. Okay, as regards the global Lipschitz regularity, the theorem is the following. So we suppose that the comparison principle hypothesis hold. We consider f globally Lipschitz function. Then any solution of the Kolmogorov equation with lambda, and of course, so also the classical Kolmogorov equation, but we need the lambda term in order to give the proof, is globally Lipschitz in the space variable, at least locally uniformly in time, but global in space. Okay, we give a little sketch of the proof. So we want to prove that the Lipschitz inequality is satisfied for the function u. And this is equivalent using Young's inequality to prove that u satisfies this other estimate. So, of course, the first one implies the second using Young's inequality. And from the second, we can obtain the first with delta equal to the absolute value of x minus y. Okay, what is the idea? The idea is similar at the comparison principle. So we consider t bar, x bar, y bar as the maximum point of the following quantity. So we have u at x minus u at y, minus the term we are interested to, minus two coercive terms, so one in the space variable and one in the time variable. And then we argue as in the comparison principle. So the idea is the ideas are the same, and we can skip the rest of the proof. Okay, we give a remark. In the first order case, the Lipschitz a Lipschitz estimate in the space variable implies a time Lipschitz regularity, because of course in the transport equation the derivative in time is equal to the scalar product of b and the gradient of u, and if the gradient of u is bounded, so will be the derivative in time. Okay, now if we furtherly strengthen the hypothesis, we can prove that u satisfies a stronger estimate, the semiconcavity. So we give a definition of semiconcavity, and we have to understand why it is important to study semiconcavity. Okay, we say that a function g is semiconcave because for all x h, one of the following equivalent conditions holds true. So the first one, g in x plus h plus g in x minus h minus 2gx smaller than gh square. This is equivalent to say that there exists a constant c such that g minus c x square is concave. So g, it is not concave, but if we subtract a parabola, we obtain a concave function. This is why we use the term semiconcave. And then the third equivalent condition, G is almost everywhere twice differentiable with an action matrix smaller than C, so bounded from above. It is immediate to see that the second and the third are equivalent. We have to do some effort in order to prove that they are equivalent to the first one. Okay, so now we can see why it is important to study semiconcavity, because the semiconcavity implies that our function u will be almost everywhere twice differentiable. So the equation, also in the second order case, will be satisfied almost everywhere. And this is a strong result for a viscosity solution. And in the first order case...
Sorry, G have to be continuous and twice differentiable. Or it is nothing is said about continuity of G.
Well, actually, we can prove that the semiconcavity implies the local Lipschitzianity. So the continuity is a consistency.
But the last condition only for second derivative almost everywhere. So you can consider the function
yes, almost
which is constant on one set, another constant, another set, and its derivative is 0 and almost everywhere.
Almost everywhere, yes.
But it is not semiconcave. Or it is semiconcave. Ah, it is. Okay, thank you.
Yes, yes, it is. It is almost everywhere.
So it is not continuous.
Well, okay, I see your point. No, okay, maybe we have to check to require also continuity here, because this definition implies local Lipschitzianity. So it is important that we have continuity. So yes, I forgot to write here, but also continuity.
Thank you.
You're welcome. So, so it is important to, so semiconcavity implies almost everywhere twice differentiability. And this is a strong result in the second order case and also in the first order case, because in the first order case, we have, we can have twice differentiability with an equation which involves just first order time variable. First order derivative, sorry. And we have this remark that in the first order case, unless very strict conditions hold, for example, when B is a constant vector field, the almost everywhere twice differentiability result is the best we can obtain. So this result cannot be improved. Okay, the theorem is the following. So we suppose that the comparison principle hypothesis holds true. We suppose that f is globally Lipschitz and a semiconcave function, and that B and sigma belongs to this Sobolev space. So they are twice differentiable almost everywhere with bounded derivatives. Then every solution of the Kolmogorov equation related to lambda is semiconcave in the space variable. Okay, we give a sketch of the proof. The idea is borrowed by Ishii-Lyons, which proved that the semiconcavity in the elliptic case. So we generalize it in the parabolic case, and we follow the ideas are similar to the Lipschitz case and the comparison principle case, but now we have to triplicate the variable. So there are more technicalities which need to be handled. So we want to prove that for each delta greater than 0, and these inequalities is satisfied. These inequalities implies the semiconcavity with a wise choice of x, y, and delta. So if we choose x equals z plus h, y equals z minus h, delta equals h squared, we can obtain the semiconcavity estimate. Okay, so now we want to work with this quantity. So we want to compute the maximum of this quantity with the function phi defined in the following way. So the term we are interested to and two coercive terms as always. And then the proof goes along the same lines of the comparison principle. Okay. This concludes the first part. In the second part, we will see an application to random time dynamical system. So now we focus ourselves on the case A equal to 0. So from now on, U and X will always be solutions of the ordinary differential equation, so the deterministic dynamic and the transport equation. So now we want to study what happens to, what can we say about the asymptotic behavior of U with a random time change. So we want to work with an asymptotic decay of U. So the first theorem guarantees us an exponential decay for the function X and for the function U. Okay, we suppose that the comparison principle hypothesis holds, so we have these equations are well posed in the viscosity sense. And we suppose that these inequalities is satisfied for the drift B, for a certain constant C, and for a certain X0 in RD. Okay, then we have an exponential decay of the dynamic capital X towards X0, and an exponential decay of the function U towards f of X0. Of course, the constant of the decay will depend only also on beta, which is the Holder coefficient of f. Okay, we skip the proof, which is quite easy. And with this hypothesis, so we have an exponential decay for the function u. Okay, the problem is the following. If we consider a random time change E of t and the perturbed solution V defined as the average of U with the random time change, what is the asymptotic behavior of V? Does it coincide with the behavior of U, or it will be different? We want to answer to this question when the random time change is the inverse subordinator of a compound Poisson process. So this is a work in progress, and we start this is the starting point of the second part and the last result of this talk. Okay, first we give some definition. We have to define what is a subordinator. We start with the definition of Levy process. So we consider omega fp a probability space. Actually, we will need a filtered probability space with the dynamic capital X adapted to this filtration. Then a process capital S T is said to be a Levy process if the following conditions are satisfied. So S at time 0 is equal to 0. S of t plus r minus S of t has the same law of SR. Then S of t plus h minus st is independent of this filtration generated by S of r for r smaller than t. So the change between st plus h and st depends only on, it is independent of what happened before. And then the third condition, t in st is a CAD-lag function, so continua through a limite à gauche, right continuous with left limits, almost surely. If these three conditions are satisfied, S is a Levy process. In addition, if t to st is almost surely an increasing function in time, then the process is called a subordinator. So a subordinator is just an increasing Levy process. Okay, and in this case, we denote by capital E the inverse subordinator of S. So we define the inverse process E in the following way. So E is the first time when S is greater than T, or if we want, the last time when S is smaller than T. Okay, now we need these other two definitions in order to define the compound Poisson process. The first definition is in order to give the definition of discrete Poisson process. So a discrete Poisson process, capital N with rate lambda, is an increasing Poisson process which values in the natural number. such that at initial time it is equal to 0, and t minus ns is independent of ns and has a Poisson distribution with parameter lambda t minus s. Okay, now we defined a compound Poisson process. Compound Poisson process is an example of process with jumps. So S of t is defined as the sum of some jumps. The jumps are non-zero and non-negative, independent and identically distributed, and independent also of the number of the jumps. And the number of the jumps is represented by a discrete Poisson process with rate lambda. Okay, the last result we want to prove is the asymptotic estimate of the function v, so the function u with the random time change. So we suppose that S is a compound Poisson process with rate lambda. We suppose that the jumps Ri have a finite moment of order alpha. Then the decay of V towards F is a power decay, is at least a power decay of order alpha. In addition, if the jumps satisfies a stronger integrability, so if there exists delta greater than 0, such that the average of this exponential is smaller than infinity, then V satisfies, V has an exponential decay towards f of x0. Okay, we give a proof of this, a complete proof of this theorem. We start from the exponential decay of u here. So we have this exponential decay. For the function we will have the same decay, but now we have to put here the average of the random time change. So in this way. And now we want to estimate the average term. Okay, we use the relation, since E is the inverse subordinator, is the inverse process of S. This relation holds. And we can estimate the average term in this way. So it is the integral of this probability. Actually, this integral will go just from 0 to 1, because when r is greater than 1, this probability is 0, because we have an exponential with a negative exponent. And so this is the probability of E of t smaller than minus logarithm of r over c beta. And so we use this relation to transform this probability into this one. Okay, now we have to estimate the term in the integral. So we have to estimate in general the probability of S of z greater than t. We can split the probability with the sum of the probability to have exactly k jumps and the probability of S of z greater than t when the jumps are k. And of course, in this case, S of z is the sum over I from 1 to k. And this probability is, since n of z is a Poisson random variable of exponent lambda z, it is the following. Okay, now we can substitute this estimation here. We have the integral of this sum. Then we do a change of variable here, y equals to minus lambda s. And so we can exchange the sum and the integral. We put all these terms outside the integral, and the integral is the following with random time change. Okay, now we want to estimate, to calculate exactly the terms in blue here. We can calculate these terms using the density of a gamma function here. And so we can calculate this integral. We obtain the following value. So now we substitute, we start from here. We substitute to the average, we substitute this term. Then we substitute the parts in blue with this estimation, and we have this estimation for the decay of V. Now we want to study this part, which includes the time. So in order to study the asymptotic decay in time. Okay, now we use our hypothesis. So if the jumps I have a finite moment of order alpha greater than 0, we can use Markov's inequality to estimate this probability. So we have a power of order alpha here, and we compute this sum. We obtain k to alpha plus 1 and this average, which is finite because R have a finite moment. And then we have this power decay. This is a power decay of order alpha. This series is converging because this term is smaller than 1. And so we have proved that the decay, it is at least a power decay of order alpha. Okay, finally, if this other hypothesis is satisfied, so e to delta r as a finite, as is integrable for a certain delta greater than 0, then we fix eta smaller than delta, and we can apply of course Markov's inequality with this function. So now we have a power decay here. We have this average. Since the jumps are independent, we can split this average here, and now we obtain this estimation for the decay. So we have an exponential decay here. This series is converging if we choose wisely the value eta. We choose the value eta such that this term is smaller than 1. And so we obtain the exponential decay, and we conclude the proof. Okay, of course, this part is, this is just a first result. Many open problems are left. Our idea is to study what happens when the U has not an exponential decay. So maybe a power decay, or maybe U is coercive, so it converges to infinity. Another idea is to study what happens when we do not have a compound Poisson process, but a more general kind of Poisson process. Okay, and this is the end. I always conclude my talk, it is a tradition, with a picture of my town in southern of Italy. So thank you.
Thank you so much, Michele. Any questions?
I have few remarks.
Yes.
First of all, concerning first part, naturally, talk is divided in two parts, as Michele said already.
Yes.
First part is very nice work in PDE, very fundamental, I like very much. Only one historical remark, because I'm old man, I can remember something. This concept of viscosity solution actually was introduced by Olga Oleinik from Moscow in 60s with another name, but it was such notion. After co-workers of Oleinik, Khrushchev and other people developed this quite good. And after Lyons, of course, ignoring history, because he is a great man, yeah, he do not oblige pay attention. So this is a small remark, it is not essential. Concerning second part, I have more essential comments. First of all, Michele introduced concept of inverse subordinator for Poisson process, yeah?
Mm-hmm.
In each book about subordinators is written that Poisson process is example of subordinator, yeah? Compound Poisson process. But it is really surprising that inverse So inverse subordinator for Poisson or compound Poisson is not well known, yeah? And we see in calculation of Michele that it is non-trivial question how to estimate influence of such inverse subordinator. I think so this moment we should estimate properly and to think about application of inverse Poisson to other problems what we discussed with Jose Luis and so on. So it is interesting class of inverse subordinators. We introduced with Kochubey and Jose Luis da Silva 3 classes of inverse subordinator. We study effects and so on, but it is new class and effects are very different, and I think so it is reasonable to apply to other kind of dynamical problems. It is remarked first of all to Jose Luis da Silva. Secondly, of course, you did mention that you're supposed to work with another inverse subordinators, yeah, for transport equation. I think so. It is also important direction what we should not forget to see that different classes of subordinators will give different effects. Probably from point of view of applications, from point of view of physics, it is most essential moment. Yeah, how you can change dynamics using different classes of inverse subordinators. Yeah, I hope we will continue discussion in this direction. Thank you for very nice talk.
Thank you, Yuri.
Thank you.
Any other comment, questions?
Jose Luis, are you here?
Yes, he is here, but he's on the test or on exam, and he can't speak. He wear a mask, so he is really on duty now. Well,
okay, I will discuss with him. No, Michele, really, it is reasonable to look how will work your class of inverse subordinators for other dynamical problems, what we discussed, for Markov, general Markov dynamics, and so on. We have a lot of concrete examples we studied already, yeah, for our class of subordinators. But how your class of subordinator will work, it should give new effects, I hope.
Yes, yes.
Okay.
But the idea was to work with the 3 classes of subordinator you studied in the article with Cesaro Min, but not with the specific function U, but in the general case of transport equation. Maybe it can be done also a generalization for the second order case, but maybe it is a second step.
Yeah. We should discuss, of course.
Yes, of course.
Yes, indeed.
Hello.
Okay.
You did very good work. You
Thank
did
you.
very good work, and I'm happy. First part, of course, should be published separately in good journal in PDE, and second part we should extend probably and discuss together new aspects.
Perfect. Thank you.
Maybe I have a question about the first part.
Yes.
If you consider the second order part in divergence form, not in the form you studied, but in the divergence form, will you have similar results?
Okay, the part with the Hessian matrix or with the gradient? So here is here.
Yeah, instead we obtained Laplacian if we replace the Laplacian with the divergence form observator.
Yes, we have
with not so regular coefficients. Let's say only Lipschitz coefficient or Hölder coefficient.
Okay, so the divergence here, instead of the trace, divergence of A, gradient of U, you
Yes,
see?
yes.
Okay. Well, of course, it is studied with the notion of weak solution and not viscosity solution. For the viscosity solutions, I think that it can be studied in the same way. Of course, if A is differentiable, we can split from one part to another. We can pass from one part to another. So also in the Lipschitz case, I think that it can be done. Well, if A is just older, then the divergence case is not equivalent to the trace case. Maybe with an approximation method it can be done because if A is smooth, or if we want Lipschitz, the two definitions
If
are.
A is smooth, no problem, but you can rewrite this equation in your form. But if it's only further continuous, then you can't.
Okay. I have to think about it, but my idea is to work with approximation. So we take AN, a sequence of smooth functions. In that case, we have a viscosity solution also for the divergence form. Of course, we need to reformulate also the definition here because we don't have any more an Hessian matrix here, but we need to work also with P here because we have the gradient. Well, we cannot write the divergence of the gradient. So the divergence means we have to differentiate. So we cannot use this definition, of course. We have used the definition, the first original definition with the test function.
Yeah, but the first definition, the original definition does apply, so we can use it.
Yes. This definition still applies. Well, in the approximation method, actually, we use this definition, so maybe it can work. But yes, I think it can be done by approximation. Maybe in the articles of Guy-Barthes, it was already done. I don't know. I have to check. But the idea for me is to work always with approximation.
I see.
I would like to give additional comment.
Yes.
Situation is the following. Why it is so difficult to study transport equation? Because it is hyperbolic equation, first order equation, yeah? And contrary to parabolic case, you cannot expect somehow bigger smoothness of solution because of parabolicity, yeah? And standard idea here in probabilistic approach was due to Wenzel and Friedland. They have book about random perturbation of dynamical systems, and they propose obvious approach. You have hyperbolic equation, first order. You put small Laplacian in front. You have parabolic equation. And if your coefficients are smooth, for me, non-smooth case is not interesting now. Just assume coefficients are smooth and Lipschitz and bounded. Then you can solve parabolic equation and show convergence of solution to the limit. It is such parabolic or diffusion approximation to solution of transport equation. And Wenzel and Friedland did it under very strong assumption about drift. And recently with some of my students, we considered result of Wenzel and Friedland for more general class of drift. Actually, Michele used this condition similar to dissipativity of drift, yeah? For dissipative drift, you can have any growth, any polynomial growth at infinity. Only important is direction of this growth, yeah? And in mathematical physics, such kind of drifts are very essential, especially in statistical physics, yeah? because they came from gradient of some polynomial Hamiltonians. Yeah. So I think so that people in classical PDE are concentrated on the case when drift is not smooth. If drift has singularity at 0 and so on, yeah, it is specific question for people in PDE. They are looking as Soviet Komsomolцы. They produce problem and after try solve such problem, yeah.
It was because boundary conditions. Usually we have some non-trivial boundaries, and therefore we have
They have
scientific
very specific own question. But from point of mathematical physics, most interesting the case what Michele consider when we have, assume we have smoothness and so on, but we have not boundedness. Yeah, we have drift which can grow, but right direction. Yeah, in right direction. I think so. This moment, unfortunately, was not analyzed in PDE. From point of view of dynamical system, it is absolutely natural. How to produce a priori estimation for behavior of dynamical system? You should look standard way. You should look to proper Lyapunov function. Yeah, if you have good Lyapunov function, you have bound. And exact dissipativity condition give us possibility to use standard Lyapunov functions. Yeah.
Yeah.
So I would like to stress again that non-smoothness is interesting case, and I understand Andrei why he asked this, because he is keen in this business with non-smooth coefficients and so on. But even for smooth coefficients, not everything is clear. Yeah. Thank you.
I just wanted to add a comment to Yuri's comment. In fact, the ultimate question is what kind of thermodynamic transition, what we are going to put to infinity.
Yeah.
Because what you insist is a kind of the size of a system, number of nodes in a graph, or should go to infinity. It's kind of well, classical approach in a sense. Number of particles should go to infinity.
Yeah.
But it's also there also another possibility, kind of considering infinite paths on a finite graphs or systems. Dynamics itself, evolution itself is infinite in time.
Yeah.
Time goes to infinity rather than number of particles. And so this is ultimately, I guess, the difference in mindset.
Yeah, I agree.
Okay, thank you so much, dear friends. I'm really happy that you come this time. So as usual, I applaud everything. I applaud our talk on Michele's talk on the web page. And next time we have Yuri with spectral analysis of non-local Markov generators. And then we have Vitaly from Toronto on the 28th of May. Yuri would speak on the 21st of May, right? And Friday, 2 weeks after, we have May 28th, Vitaly Vugalter on the solvability of some systems of integral differential equations with anomalous diffusions in higher dimensions. This is a hardcore PDE theory.
I have only one doubt. If people will be happy that you have so much Yuri, too much talks from me.
So what
is never too much.
Yeah,
what is the problem?
Completely another direction, completely another topic. Yeah.
Well, absolutely. I like actually next topic so very much. I mean, it's for me, for my research is very important and interesting.
I hope people will be stable enough.
Okay, thank you. Have a nice week. All the best. Take care. Stay safe.
Greetings to
Yeah.
everybody.
Well,
Bye bye.
greetings. Bye.
Bye.
Right.
Thanks. Bye-bye.